It's terrible, terrible anchor grinder. Probably 2, 3 years ago, maybe 3 years ago. Didn't think it was any use. Didn't think it was useful at all. It claims to be USA, claims to be 800 watts. Sure, right. It's a cheap Chinese piece of crap. I bought strictly for that 90 degree. A project at the time I wanted to do. I needed a 90 degree. Couldn't find anybody with an old angle grinder that was there that I could have taken, the gear. And this is the cheapest way to get a gear. Cheapest way to get a reasonable 90 degree gear that wouldn't break on you. For what I was doing, it wouldn't be the torque. I didn't have that. So I expect that this doesn't have any kind of power to it. It's 800 watts here. We'll go back to that anyway. So the next thing is the two brushes here, right? A very, very cheap plastic, of course. What I want to try and find out is this a universal motor? I think it should be a universal motor. It makes sense to be a universal motor. So the fun part, let's connect it to 12 volts. Let's see if you can get it to spin at 12 DC. Computer power supply, try 12. I tried 24. That blue is minus 12. This is positive 12. So 24 volts. No luck. Switch is on. I'm getting current flowing. I'm seeing the sparks, but no luck. Let me check and see what the resistance of this is, so we have an idea of what we're working with. And then probably just open it and see. Maybe I'm wrong. Maybe it's not a universal motor. Enter it. Let's see. I'm getting 38 ohms. So it's a fairly high resistance. Yeah. Let's call that 40. That gives us 3 amps. At 24 volts, that will probably what? That's less than a little bit over half amp, isn't it? Yeah. So, yeah. Maybe not anywhere close to enough torque. This is relatively stiff, so maybe not enough torque to turn this. They didn't mention the grease. There's a lot of grease. Maybe crappy grease, don't know, but there's a lot of grease. That's a little pin that fits into one of these 2 notches to hold that gear, so you can tighten and loosen. And yeah, as I thought, the gear is pretty strong. I mean, it would have been perfect for the application I had in mind. This was not going to break. So let me try it now, because it's a lot less torque. I do not know if this had a bearing in there. Can't really properly see. Yeah, there's a bearing in there. There is a bearing. So it's not just a bushing. You can never tell with the Chinese, right? But anyway, let me try to run it now and see if I can get it to work. No luck. So maybe it's not universal, or maybe it's really 24 volts is just way too low. Well, interesting. We actually have a bearing at the end. We have a bearing at the top there. This is a bit dodgy, but I guess it sort of works. Somebody tried to balance this by drilling some holes. Not fully drilling through, just kind of notching it. An interesting approach. I mean, really, what can I say about that? Really. Very, very small coil, right? If we look inside here, another very small coil. Let me swipe it on the light. Right, jumping back in, very small coil inside here also. Clearly, definitely a universal motor. So yes, just really too low voltage to make it spin. That said, yeah, there's so much space inside here for more coils, and they've chosen to not put it and make it very cheap. I mean, it's just right here, and it could have been all here. This again could have been all that. All that could have been coils. A lot more interaction, a lot more power, a lot more copper, a lot more course. Chinese, right? The epoxy here that they used isn't that well done. I don't know if it's visible, but it's a bit dodgy. It's looking like it's reached its life, and they've just packed it in. Someone tried to balance this at least also with an angle grinder, it looks like, and they've just cut some notches on this side and some notches on this side to balance it all off. So at least there is some sort of dynamic balancing. And I don't know what you want to call this dynamic balancing too, but some sort of balancing. It does not appear that this will come off easily from there. Not that it's helping that much. I mean, if you consider this is a really small coil, low gauge wire, yeah, not the best done. The brushes aren't half bad. I mean, they're not great, but they're not. It could have been worse, right? Let's just put that way. It could have been worse. So yeah, it could have been a little bit longer. Chinese, very cheap thing. So yeah, all in all, I guess kind of what I expected. And yes, it is a universal motor. I am not sure what power it really has and how long this could really run and if I can use it. But this piece definitely. In fact, this turned out to be better than I even anticipated. The length of this shaft means I could have cut this here, had a very good extension to do my little project. In fact, I only need up to about here, and I expected this coil was going to be up to about here. But yeah, very good extension, spine, and a very easy way to join on. It looks more like a bolt than anything else. This would have been really good for my project that I have not gotten into and probably will not. That said, still is a good motor in case I want this 90, because there's a possibility that somewhere along the line I'll try to build some sort of boat, a remote control boat, and if I do, and I do get the time, that's a big if, this is a perfect 90 degree for my impeller to go down in. Yes, it's not stainless steel. Yes, it won't last that long in the sea, but perfectly good clamping mechanism, perfectly good place to put our impeller. Could work out very well, and a long shaft that I can cut from quite about here and get another bearing, stick that in there, and still use this motor for something else. Just cut this off and yeah, just make up a house, and or just cramp this down, cut it off, or put in some sort of bearing in there and make this work. So this could still work for me. It could still be repurposed for multiple things. This up now. Let me have a look and see if I can figure out what the inductance of this is. So I have my LCR meter here, and it's coming up at 13.9 milliohms. So let's call that 14. Let's see. Right, we go to, well, it doesn't make sense that we don't need nanofarads. Right, ohms according to this is 95.56. So not actually the same as we got with that meter. This is supposed to be a good meter. This is supposed to be a much better reading. So we're saying 96 ohms, and we're saying an inductance of, let's see, come on, 13.9 millihenries. Based on the readings we got, let's do a little quick calculations. So what we need to do is calculate the inductive reactance based on the 14 millihenries we measured. The inductive reactance is 2 pi FL, frequency being 60 Hertz. So it's 2 by 3.14 by 60 by 0.14 because it's millihenries, and that needs to be in henries, which turns out to be 5.27 ohms. Using the last value that we calculated for inductance into the formula for the impedance of the circuit, the AC impedance, what we use is the resistance of the coil squared plus the inductance squared, square root of that. So it's square root of, in brackets, 5.27 squared plus 95 squared, and that works out to be around 95 ohms almost, because the larger value will obviously take precedence when we do an equation like that. At 115 volts, that works out to be 1.21 amps. Running the same calculation using the clamp on meter reading, we see if we use 38 ohms approximately, it comes out to be almost 38. Again, the larger value, when you do a squared and square root, it will take precedence and it will be pretty much close to the large reading from the large value. And working that back, it works out to be 3 amps. So let's run a test and let's see what we get. Let me throw this on. Hopefully it doesn't jump anywhere. And let's see what we get. After doing some initial calculations, it became obvious that, well, those initial readings were definitely wrong. So let's look back at this thing. 49.56 ohms. As we switch on, rotate the wheel a little bit, and we get different readings. And let's look at our LCR, and we're getting, why am I getting 30 ohms here now? Interesting. 20.4 millihenries. This is not working out well. 19, 17, 19, 21, 20. So yeah, apparently this is saying 18 to 20, so let's put it at 20 millihenries. 20 millihenries. We're going to work with that. Yeah, that's fine. That's fine. Let's move on. 66 ohms. Interesting. Resistance keeps changing. Wow. 74, 66, 58, 63. Higher end looks like about 70. So, okay. We go with 70. Let's do a rough calc with those numbers and see if it matches up our current. Using the readings from the second time, what we're looking at is we're assuming 20 millihenries and we get 7.5 ohms, and then going with the 70 that we picked up, what we end up with is 70.4 total impedance. And as I said, larger numbers going to take precedence. Dividing that out with the 150 nominal goes out to 1.63 amps, which kind of matches a lot because running startup will obviously be a little bit higher. Running it, we got the value down in the end to 1.67. That's as good as you're gonna get with theoretical and trying to measure in the real world. Close off everything. What we're gonna try to do is see if I can figure out what voltage this thing really starts at. Right, this is a dimmer attached to a plug, and I just have this to turn down the speed of some of these devices, something like this, that will be problematic. And then what we have is the meter plugged into the other plug. So essentially speaking, it's the same 0.356 volts, so clearly that's a low. Let's see, when it starts, I'll see what voltage it reads. Maybe this is, alright, well, that's 10.9 volts AC, that doesn't make sense, let's see. Oh, right, there we go, 48 volts, 48.3 volts, but that's the voltage it starts at. You see how low it can really go. Alright, it jams at 25 volts, completely jammed. Let's see. Just barely starts at 50 volts. So yeah, universal motor, but it just didn't have enough high enough voltage to start.